There is no such thing as a typical alien. The image of a grey-skinned humanoid with large eyes, that's not science. That's a mirror. We imagine aliens that look like us because we can't help it. But the universe has no obligation to repeat our design. And the real answer to what alien life might look like is far stranger and far more wonderful than anything Hollywood has ever imagined. To understand why, we need to think carefully about how evolution works and what it might do on a world very different from our own. When scientists think about the possible forms of alien life, they start with a fundamental question. How much of life's design is contingent, the result of historical accidents that could easily have gone differently, and how much is convergent, the result of universal physical and chemical constraints that would push life towards similar solutions regardless of where it evolved? The answer, based on what we know from life on Earth, is both. And the interplay between contingency and convergence is what makes the question of alien life so fascinating and so genuinely difficult to answer. Let's start with convergence. On Earth, we see it everywhere. Eyes have evolved independently at least 40 times in different animal lineages, from vertebrates to insects to mollusks to worms. The basic design of a lens focusing light onto a photosensitive surface is such a good solution to the problem of detecting light that evolution keeps reinventing it. Wings have evolved independently in birds, bats, insects, and pterosaurs. Streamlined body shapes for moving through water have evolved independently in fish, dolphins, ichthyosaurs, and penguins. The same solutions keep appearing because the same physical constraints keep applying. Evolution, it seems, has a limited number of good answers to the problems of survival, and it finds them repeatedly in different lineages on different timescales. This principle of convergent evolution suggests that on other worlds, life might independently arrive at some of the same solutions that life on Earth has found. If a planet has a star, photosynthesis, or something like it, might evolve. If a planet has a fluid medium to move through, streamlined body shapes might appear. If a planet has complex chemistry and the need to process information, something like a nervous system might develop. The laws of physics are the same everywhere, and those laws constrain what works. Life on other worlds might be alien in its details, but familiar in its broad strokes. But here's where it gets complicated. Convergence operates within constraints set by the environment. And the environments on other worlds may be radically different from Earth's. Different gravity, different atmospheric composition, different energy sources, different chemistry, different day length, different seasons, different temperature ranges. All of these factors would shape the evolutionary pressures that life faces, and therefore the solutions it develops. Consider gravity. On a world with much lower gravity than Earth, large body sizes might be more easily achieved, or the constraints on body structure might be completely different. On a world with much higher gravity, life might be flatter, more spread out, hugging the ground. On a world with a thick, dense atmosphere, flight might be trivially easy, and the skies might be filled with creatures that never touch the ground. On a world with a thin atmosphere, flight might be impossible, and life might be confined to the surface or the oceans. Gravity shapes everything: the size of organisms, the structure of their skeletons, the way they move, the way they reproduce. Change the gravity, and you change the entire blueprint of life. Consider chemistry. Life on Earth is carbon-based and uses water as its solvent. But are these the only options? Silicon is sometimes proposed as an alternative to carbon. It forms long chains and complex molecules, though not as readily as carbon. Ammonia has been proposed as an alternative solvent to water. It is liquid at lower temperatures, which might make it suitable for life on cold worlds. Titan, Saturn's largest moon, has lakes of liquid methane and ethane on its surface, And some scientists have speculated about the possibility of methane-based life, organisms that use liquid methane as their solvent and breathe hydrogen instead of oxygen. These are speculative ideas, and there are serious chemical objections to each of them. But they illustrate the point. The universe of possible biochemistries is larger than the one example we have. Life on Earth is not necessarily the template for all life everywhere. Consider also the role of time. Life on Earth has had 4 billion years to evolve. In that time, it has gone from single-celled microbes to organisms capable of building telescopes and asking questions about the universe. But evolution is not a straight line. It is a branching, contingent process shaped by mass extinctions, climate shifts, and random mutations. The specific path that led to humans was not inevitable. If you rewound the tape of life on Earth and played it again, you would almost certainly get a very different result. The same is true on other worlds. Even if the broad constraints of physics and chemistry push life towards certain solutions, the specific forms that emerge will be shaped by the unique history of each world. What about intelligence? If we're asking what alien life might look like, we have to ask whether intelligence, the kind of complex, abstract, tool-using cognition that humans have, is a likely outcome of evolution or a rare accident. This is one of the most debated questions in astrobiology. On one hand, intelligence seems to be convergent on Earth. Octopuses, which are mollusks and share no common ancestor with vertebrates for over 500 million years, have evolved remarkable cognitive abilities, problem-solving, tool use, complex behavior. Corvids, crows and ravens, have cognitive abilities that rival those of great apes. Dolphins, elephants, and great apes all show signs of self-awareness and complex social intelligence. Intelligence seems to keep evolving, independently, in different lineages. On the other hand, the kind of technological intelligence that humans have, the kind that builds cities and telescopes and spacecraft, has only evolved once in the 4 billion year history of life on Earth. That might mean it's rare, or it might mean we just haven't been around long enough to see it evolve again. The honest answer is that we don't know, and we won't know until we find life elsewhere and can compare notes. What we can say is this: if life exists on other worlds, it will be shaped by the specific conditions of those worlds. It will be adapted to its environment in ways we can partially predict and partially cannot. It may be microbial, simple, single-celled, invisible to the naked eye. It may be complex and multicellular. It may be intelligent. It may be something we don't have a category for. The universe is 14 billion years old, and some of the worlds out there have been running their evolutionary experiments for far longer than Earth has. The diversity of life that might exist across the cosmos is almost certainly greater than anything we can imagine from our single example. If you want to keep exploring these ideas, subscribe and stay with the playlist, because in the next episode, we're going to ask what it would actually mean to make contact with an intelligent civilization beyond Earth. Contact with an alien civilization. What would that actually look like? That's next. Subscribe and keep watching. This is where it gets really interesting.